Okay, guys, welcome again to G Squared Academy, where we know excellence is invariably epitomized. So, as you can see on the screen, what we want to look a little bit at today is Le Chatelier's principle. I am not French, of course, so that's my best French pronunciation, Le Chatelier's principle. And of course, this has to do with equilibrium on a whole. Um, and so generally we want to look at it. First of all, let us state what is Le Chatelier's principle. And without getting too technical, we're basically saying that the Chatelier's principle is this. If a system is in equilibrium and a change occurs within that system, there's some stress added to the system, then the system will do whatever it can to counteract that stress to re-establish equilibrium. Okay, so whatever happens to the system, of course, if you change the temperature, you're going to change the equilibrium constant. So except for changing temperature, whatever else you do to the system will try to counteract it pretty much to re-establish equilibrium. So now it says here, describe how the following equilibrium would be affected by the proposed changes. So the first one, you have an increase in pressure. So you have increased the pressure on the reaction pretty much, right? So look at it now. What you have here, and let me just highlight these things. What we have here now, um, what we have here, yeah, is 2 moles right there and one right there. So that's 3 moles, and there are 2 moles of gas on the right. So clearly you have more moles of gas on the left hand side of the equation. So if you increase the pressure, the system is going to say, why did you increase the pressure? We need to now decrease the pressure. And so to decrease the pressure, you need to go to the side where you have less moles of gas. And that would, of course, be on the right hand side. So therefore, the reaction would proceed to the right. Okay, and so the forward reaction would be favored, and you'd be getting more SO3 gas being produced. Okay, the second one, you don't have to consider the delta H over here because you're changing the pressure. You're not looking at the temperature. A decrease in temperature on the equilibrium. So for this reaction now, they're looking at temperature. How would temperature affect this reaction? Now notice that this reaction is exothermic. It has a negative delta H, which means that, quote unquote, it produces heat, or heat is released into the surroundings overall at the end of the reaction, or while the reaction is being process, right? So you decrease the temperature. The system is saying, we don't want you to decrease the temperature. We want to increase back the temperature. So the reaction will proceed in the direction which produces heat, which is the forward reaction. And so therefore, more ammonia would be produced because you are trying to increase back the temperature. All right. Now, the final one, and of course, the opposite is true. If the forward reaction is exothermic, then the reverse reaction is endothermic. And if you were to increase the temperature, then the system would look to decrease it, and so the reverse reaction would proceed. Finally, an increase in pressure on the system, which is pretty much similar to the first one, an increase in pressure on the reaction. Now, in this reaction, though, what you have, let me undo a couple of things there so we can get, yes, there you go. What we have now is 1 mole of gas there, 1 mole of gas there, and 2 moles on the other side. So on both sides of the equation, you have 2 moles of gases. So pretty much all that's not going to have an impact on the equilibrium because both sides have equal number of moles of gases, and so therefore if you increase the pressure on the system, all you're going to be doing pretty much is forcing the reaction to proceed equally in both directions. So therefore no real change would occur on the system itself, on the reaction itself, or even on the system in this case. Okay, so that is Le Chatelier's principle for you in a nutshell, and I hope you found this helpful. This one is not there, but if a catalyst was involved and they ask you how the catalyst affect the rate of the reaction, not the rate of the reaction, the equilibrium constant, it does not, because the catalyst simply allows equilibrium to be established faster. It doesn't affect. It does not affect the rate of the reaction. It does not affect the equilibrium constant. Okay, so that would be the situation with the catalyst. And of course, pressure, this is a gaseous system, so pressure is pretty much the same as concentration. If you change the concentration, then the system will do something in order to counteract that change, similar to pressure. All right. Thank you guys, and all the best.